can find this little bullet point to-do list on the course outline for all your subjects. Sometimes it's really helpful because you're seeing things from another point of view. Sometimes it's not helpful because it's quite vague. Like chemical equilibrium systems, that's very vague, right? What does that even mean? Okay? So sometimes it's great and sometimes it's not so great. But it's another tool that you can use if you want to. All right, so over here, all right, and I'm going to write the first one. So what do they mean by chemical equilibrium systems? Okay, so what does that mean? What does that symbol mean? Reaction goes both ways?
Not all of the reactions react.
Some concentration of products and reactants present, right? So that first, that's kind of just saying what you said, I'm just saying a bit different. So some products and reactants are still in that flask, always. What do they mean about rate?
Are the same.
Right, the forward and the reverse reactions, their rate is equal. They have an equal rate. That means the speed. The speed in which this is happening is just as fast as the speed in which that is happening. Okay? The rates are equal. What does the concentration? So if we have A plus B goes to C, and I have a little bit of each, are the concentrations equal? The rate is equal. The rate of the forward and the rate of the reverse are equal. Are the concentrations equal? No. So the concentrations are different. The concentrations are different depending on whether it favors the reactants or products. So if it, yep, these aren't notes, these are just chatting. So
I'm sorry, I'm confused when it says, doesn't it say same concentration of products and reactants present?
no, some.
Oh.
There is some concentration of the products and some concentration of the reactants present. A little bit of everything, but not equal, not the same, no, some. The concentrations are different.
Yeah.
If it favors the reactants, then I have more reactants present. If it favors the products, I have more products favored. Who up there mixes up the words products and reactants all the time? Yeah, me too. Me too. So if you get a question that's talking about reactants and products and you're the type of person that mixes it up, you need to write this somewhere in your paper so that you kind of go reactants on the left, products on the right. Okay, I'm not going to make that mistake. I still know the information. I'm still going to get the answer right, but I'm not going to let my muddling up of the word reactant and product get in the way of getting the right answer because I know what that means. I mean more concentration of this stuff. What's that stuff called? Oh, products. Okay, good. Okay. What does dynamic mean?
Always changing.
Always changing. So if we were to radioactively tag one of those chemicals, we would find it pop over here, pop over here, pop over here, pop over here, right? And what's the Chem 20 foundational example of what a dynamic equilibrium is? Shut your phone off, whoever that was. What is the Chem 20 example? Dynamic equilibrium. Radioactively tag it. Saturated solution. Thank you. I'm so glad somebody I taught Chem 22 came up with that. So a saturated solution, you get some solid that doesn't dissolve, right? No matter how much you mix it, no matter how long you wait, it won't dissolve. Unless you do what to it?
Heat it up.
Heat it up. What does heating up change? The K value. That's why you can dissolve more. That's why you can get this you know, whatever it is, copper sulfate, solid, to give you more copper 2 plus and SO4 2 minus if you heat it up, because you change the K value, which changes your products divided by your reactants. So you can get more of this if you increase your K value by increasing the temperature. Oh, fancy that. That's why it works. So a dynamic equilibrium, if I radioactively tag, this is CuSO4 solid, sat there, you think it doesn't move because the mass doesn't change. That pile is the same height the whole time. Only if you could radioactively tag one of these, you would see it pop in here as a CO2 plus, and then pop back in, and then pop out and pop back in. But because the mass of that hill doesn't change, it must be a 1-for-1 ratio, or rate for rate ratio. The speed that it's dissolving equals the speed that a different one must be precipitating. Bless you. Or crystallizing is actually the better word. Everybody okay with that? So that's like your foundational of dynamic equilibrium, rates equaling, all that stuff is somewhere in a test. Right? The definition of something on there is on a test. And if you treat each question that you see as a brand new question, you will be overwhelmed. However, if you see this sheet and you go, I get everything on there, I understand everything on there, I know everything on there, then no matter what question they throw at you, they'll all seem the same.
Class change.
Because it's all asking you to tease out the difference between the rate versus concentration. Or it's asking you to tease the difference out between dynamic versus static, unchanging. Right? And they're all kind of the same thing. I mean, how many of you have seen a question or 5 that have to do with this sheet? Right? So then you group them all together as the same information that they're trying to pull out. The same bullet point on the curriculum that they're trying to ask you about in a different way. And then you'll see it as just one thing, not 10 things that you need to know. Just one thing. Oh, I could do that. I can do this one thing. Okay. Everybody okay with that? Okay, so the next one thing is reversible reactions. So we actually haven't had time to do, I normally do some demos of reversible reactions, but we actually haven't had time to do any of them. We've talked a lot about them, right? So let's go back to copper sulfate, because that's on my mind. Solid. Do you know that blue copper sulfate is hydrated? So blue copper sulfate actually is dot pentahydrate. Solid. Okay? And if I heat that up, I can drive off the water, evaporate the water from it. And it turns into a white copper sulfate, solid. And can I write on that bit? Nope. And the 5 waters have vaporized. They've just gone up in the air because I've heated it up. And actually, you can see the water droplets on the sides, the mouths of the test tube. Okay. And if the mouth, so here's the test tube. Here's some blue copper sulfate. You add some heat to it. You drive off the water droplets end up here. And this ends up being now white CuSO4. Does that make sense? But eventually it cools, and those water droplets come dribbling back down. And so now the water is going to combine with the copper sulfate and now go this way, making your blue crystals come back again. Do you get that? And I could add heat and shift it this way again and make the white. And I could cool it to make it go this way and back and forth and back and forth and back and forth.
Yeah, so is that like that question on the unit test that was like, what color would it be? And then it said lighter, and like the options were like lighter than darker, and then darker, and then lighter. And
Okay, so
Are we
Do you know
supposed to
what
know the
question I'm
colors?
talking about?
That was the equilibrium shift.
okay, so that
Yeah,
is
number 2 on here.
oh, perfect. So on your exam, your unit exam, thank you, you have a full syringe of 2NO2 gas, equilibrium arrows, N2O4 gas. Nitrogen dioxide is brown, and the other gas is colorless. what is observed when the syringe is used to compress this mixture? So now this is the Le Chatelier bullet point. Everybody okay with that? This is Le Chatelier bullet point. Going back to, hold on a minute, reversible reactions bullet point, and the one just before, the chemical equilibrium bullet point, can you see that both of these things exist in that flask at the same time? Okay, so here's a flask, and it has NO2 and N2O4. So it's got some brown and some colorless. Okay? And if I can shift this equilibrium, I can make it become more brown by having more NO2s and less colorless, or less brown and it be more colorless. And everybody okay with that? Okay. So now, and this is again, now we're encroaching on the Le Chatelier's principle. So Le Chatelier said there's three things that affect equilibrium, right? What are they? Pressure, temperature, and concentration. What's the thing about pressure that we always get mixed up on? Volume. It has to do with volume and not an inert gas. So if I add gas, it will increase the pressure, but that has no change on the equilibrium. Okay, just the volume bit. So if I increase the, does it say increase on the test? Sorry, let me just read it again. What is observed when the syringe is used to compress this gas mixture? So the question says I'm decreasing the volume, so therefore it's going to increase the pressure. Everybody okay with that bit? Yeah. And if I increase the pressure, I've got a 2 moles on this side, so 1 mole on that side. So increasing the pressure is going to make it shift this way to side with less moles. Yeah. Everybody okay with that? So you're looking for it to become, hopefully not colorless, but rather a lighter brown. Hi.
Can I interrupt you for 30 seconds?
Absolutely.
So just a reminder, guys.
Okay, so lighter brown. So you're looking for the lighter brown option, and you go to the option keys, and oh, it's not there. What's there instead is the mixture gets lighter. Okay, oh, actually that is there. The mixture gets darker. No, that's definitely not right, because that means you're shifting left, and we know that that's not right. It gets darker then lighter, and it gets lighter then darker. Oh, crud, I see lighter 3 places. Okay, this is what they're trying to tease out in this question. Remember the graphs of equilibrium? And if I had my NO2 here and my N2O4 there, what happens when I change the pressure at point A? What happens when I change the pressure? What happens when I increase the pressure? It spikes. All of them spike. Right? If I'm increasing the pressure, they're going to spike up. Why? Because I've got more molecules per square centimeter. Cubic centimeter, pardon me. I've got more molecules per liter. That's why it spikes up. You've essentially increased the concentration of all of them all at once. Okay, so they spike up, and then they adjust for equilibrium. So you're saying that you're going to get more N2O4 made, so this is going to go up, whereas this is going to go down, and then until I reach a flat line equilibrium. So what actually happens, it spikes up. So it gets, that spike up would be, that spike up would be darker. I get more brown. So I get darker and then lighter.
So with any pressure change, you will always have an increase in everything?
Yes.
Immediately, like not.
With an increase in pressure. With a decrease in pressure, I get a spike down of all of them. Okay? But a spike in all substances is pressure. Okay? So I'm looking for darker goes, and then it gets lighter, so that's now C. Is C the right answer? I hope so. 2.
It gets lighter than lighter.
Darker than lighter.
And then it goes back. Brown.
Lighter than dark.
I increase the pressure, but just to make sure I've read this all right, because I wasn't really the syringe is used to compress, so I'm increasing the pressure. The pressure is going to shift to the colorless, no, it goes darker than lighter. Oh, sorry. The answer is C.
Why? I don't understand.
Oh, let's see.
Okay, so
If it's shifting that way, like, wouldn't it go lighter and then darker, because it would go back,
Yeah.
because it's equilibrium, like, it would, because if it's in favor of the products, and the products are colorless, and they would go lighter and then like
Okay.
shift back.
let's just hold on. Use your normal knowledge. Okay? Here is a syringe. Like a needle, right? And it's filled with gas. And this gas is a medium brown color.
Yeah.
I plunge the syringe. So I've squished it. Now that medium brown color should be, what do you think? Darker. But then the equilibrium shifts. And what you know about equilibrium shift is that this should shift to the colorless side. So eventually, ultimately, this solution in my syringe will be lighter in color. So it's going to go darker and then lighter. Now I agree with the sloshing back and forth bit, that does happen, but when they ask this type of question, they're looking for, and they've asked you for 2 colors, they're looking for immediate, long term.
So it's
Okay? If they're only asking for 1, they're looking for long term. Ultimately, at the end of the day, what color are you going to see? A lot lighter brown. Yes?
Why'd you mark B right on the test?
It's not, it's C.
Like,
Typo. Okay? Everybody okay? Yes?
I'm just confused because you know how when we talked about the mole ratio shift when you like increase the pressure and you said like it favors like the forward reaction, so that would
Mhm.
favor the forward reaction. So why? I don't understand why it's going darker.
It goes darker for a second, then it'll favor the forward reaction and go lighter.
Well, why doesn't it go lighter when the 2-1 mole ratio gets pushed over to the
the
right?
tube thing.
It does go lighter.
Yeah, but doesn't it go lighter than slosh back to darker? Isn't that?
And then slosh back to lighter, and then slosh back to darker, and then lighter, 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 ultimately lighter.
Yeah, like the two things. Like logically, how you explain it, that makes a lot more sense. I just thought like when
Did
like the mole
thing.
ratio thing like confused me because it's like pushing it to the right.
Okay, so this is an upper level thinking question, because the straightforward question would just say, what color does it get? Light or brown? Everybody okay with that? Everybody okay with that initial example, and then you're looking for light or brown in the question? That is the normal, straightforward, do they understand Le Chete and pressure? Okay, so, but then you realize, oh, it's got all these options of lighter. So then what it's asking you to do is tie Le Chete with the graph, or even your head, right? The syringe squishing it, visualize that in your head. And you're gonna see a spike in that color, and then it's gonna reach that equilibrium that you decided over here. Okay? Yes?
So it's not, once it's at its equilibrium, it's not going to go back to the darker.
No.
It's going to stay lighter.
Right. That's right. So this is, as soon as I squish the syringe, then I leave it for the weekend, I come back on Monday, it is going to be lighter, and it'll stay lighter forever. Once it's reached equilibrium, it stays that way. Like back to the saturated solution. Once you've dissolved as much as you can, that piled mass will stay the same forever and ever until you cause it to shift. Increase the temperature or whatever, right? Then you can cause it to shift, and then you can dissolve more, but otherwise it's going to stay that way forever. Okay? Okay, so Le Chete, anything else for Le Chete we have to know? 3 things that affect it. You need to know your Le Chete. These are the easy marks. These are the easy marks. That is not an easy mark, that question there, because it's the graph. The graphs are hard. But just simple, straightforward, what happens to this exothermic reaction when I increase the temperature? It's going to be reversed.
So the graphs are under the Chate's principle.
No, they're tying 2 subcategories. I don't know. The graphs are part of equilibrium systems, I would say. This first bit. But the shift in that graph is Le Chattier. Right? Causing the influence on that graph, that is Le Chattier. And then watching it go back into the equilibrium. Everybody okay? Okay, so I apologize for the typo on that Unit 4 exam. Not typo, the typo in the mark scheme. The Unit 4 exam answer is definitely C. Are we all comfortable with knowing how to answer that type of a question again? Okay. Okay, so I'll say this one more time because this is important. If they ask for 2 colors, they're asking for the spike and the long term. If they're just asking for 1, it's back to basics, long term. Do not make the mistake of talking about the sloshes. Okay? Do not make a mistake of talking about, that's overcomplicating it, that's not what they want. Because at what point did you pause the video in your discussion? Or when it's sloshed this way or sloshed that way? At what point? That's about it reaching equilibrium again. Okay? Yes?
So if there's like a question when they have just like one option, or like in the unit test where it's darker than lighter, there's those 2 options. Would you assume that that's what they're looking for then?
Sorry?
Do you mean? Like, because I put just went colorless, but if...
No, it's more correct. Wouldn't it be more correct if I said observe? What would you observe?
Yeah, that's what I was saying. Like,
You would have written down both things, wouldn't you have? If you were the scientist and you squished that syringe, you would have said it went darker and then lighter. That'd be your full observation list. So that answer is better than saying it went lighter. Well, what were you sleeping for a little bit and then decided to write it down? Right, so that's a better answer, so that's why you chose that answer over the lighter one. Okay? So don't make it an assumption, it's just which is the better answer of the... Okay, so back to... Any question on, do we have to do any more on Le Chattier? Are we good with Le Chattier, boys in the back? Okay. So, equilibrium law expression. What did I want about equilibrium law expression? K equals products over reactants. That's how we memorize it. What's the general K expression? It's not products, it's C
over little or
C to the power of little c
times
d to the power of little d
over
d
times,
to the power of little d.
okay? So if they ask you for it, this is what they're looking for. What we think in our head is this one, because that's helpful. This isn't very helpful. But it's more correct, because you're talking about AA plus BB equilibrium, oops, that's supposed to be a B, CC plus DD. Okay? So this is the official general expression, but we always say products over reactants. What don't we include in our equilibrium expressions?
solids if you're like
If it's a gas, to make sure it's
Unless it's, what's that word? All homogeneous. Homogeneous what? Equilibrium. And if it's a homogeneous equilibrium, then you include all things. Right? So if they're all liquids, you include all of them. But if it's a liquid and an aqueous and a solid, no, then we only include the aqueous ones. There's little subscripts that can go there. We've seen 2 of them. What are they?
So like go KEQ.
KEQ and KC. They're exactly the same thing. Don't get confused. Anything else about equilibrium law expressions? I think at this point we should probably write down if it's a large K value, then what? Favors the products. Because this is big, so this must be big and that must be small. What does favor the products mean? What does that mean? Favors the products?
Forward reaction.
Favors the forward reaction. What does that mean?
Larger concentration of the
It means ultimately, back to that first board, I have, if it favors the products, I have more products. Then I do reactants and concentration. Okay? So therefore my flask would be, if we go to this one, this flask, if it favors the products, would be lighter brown and not darker brown, or whatever. So they could tie that into a colors question. Yes?
So just to clarify, you don't use liquids unless they're all liquids, and
Correct.
you never use solids, period.
If they were all solids
Then
and they
use
asked me to
solids.
write an equilibrium expression, I would include them all.
Okay.
Yeah. Yes?
How does temperature like affect the KQ? I know that's something that affects the KQ, but like if you temperature raise, does it like raise it or?
It depends if it's an it depends if it's exothermic or endothermic.
Okay.
Okay? So, right?
Yeah.
So let's take that reaction here, and let me tell you that this is an endothermic reaction. So that means I have to add heat to it in order for it to go that way. Okay? So if I increase the heat of this system, which way will it shift? To the right. So if I'm shifting to the right, that means I'm making more of this, which means my K value would then be higher.
And that means like if you shift to the right, it's becoming more endothermic, right? Like the reaction, you're not shifting to the exothermic reaction.
Correct.
You're still shifting to the endo.
Correct. Because I've increased the temperature, so it's going, whoa, whoa, I'm going to do more endothermic then to make it cooler, to take that temperature away. Right, so in that case, your K increase in the temperature would equal an increase in the K value for an endothermic reaction. Now, you can memorize that line, but I kind of think that's useless because then you can answer one question. If you've memorized increased temperature equals increase in K value, right, for endo, and then you memorize increased temperature equals decrease in K value for exo, you can memorize those two lines. It's in your table. Remember how it made you write that whole big table down? It's in there. You can memorize that. But with that memorization, you can only answer one question. With figuring it out the way we did, going back over here, talking about endo, you can answer Le Chatier's questions, you can answer color questions, you could answer a graph question, and you could answer that question. So it's far better to understand it than it is to treat it as a memorization.
Why would it increase the K value for the endothermic if you increase the temperature?
Okay, so over here, if I increase the temperature here, it's going to shift it this way,
Right.
giving me more products.
Oh, okay.
So more products, more top value,
Okay.
bigger number when I divide them. And you know, you can answer far more questions that way. Okay?
So then would a way you could word that be, it would shift it to be more exothermic or more endothermic?
It would shift it to be more endothermic. Yeah.
To try and get rid of the heat.
Correct.
So if the endothermic is on the left side, you're saying it's going to shift towards the products?
The endothermic's on the left side? I mean, if the
Like
energy's on the left side.
Yeah,
The endothermic's
Yeah,
always on
sorry.
the energy on the left side.
the energy's on the left side, would
Yeah.
it shift towards the products? Is that
Yeah.
what you're saying?
So it's trying to balance it out.
Right.
Because I'm just a little confused because endothermic is absorbing energy, so wouldn't it want to stay in the reactant side where the energy is?
Do
That's-
way more reactants than
I'm just mixing it up.
Okay, you're mixing it up. Go back to your basics of Le Chatier.
Okay.
Okay, I could do that with you later. But it looks to me like you just need to look at a few of Le Chatier's principles to get that solid. Okay, so everybody okay with law expression? Are we missing anything? Anybody remember anything that we covered here that? I don't think so. Okay. Right, so that was the first bit of your quiz, wasn't it? Your take-home quiz. Okay, so then the next bullet point is KC, KW, KA, ooh, and KB. We've done KC, right? It applies to a reaction, any kind of reaction, any kind of system that exists at equilibrium. KW, what does it apply to? Just water?
But it also equals H times KB.
KW exists in any aqueous solution, okay? And we most talk about it with Ka and Kb. So it doesn't just exist for pure water. And you should know that because we do this formula, as you were saying, Rachel. Right? We have that formula. So clearly Kw can apply when you've got an acidic solution or a basic solution. And that is, by the way, Chem 20. So in Chem 20, yesterday, I was saying H3PO4 goes to, and really it's equilibrium arrows for us, and for them, they go all the way to the end. For us, we just do one proton, right? And I was saying if you've got a 0.2 mole per liter solution of that, you've got 0.6 mole per liter solution of that. And from that, I could ask you for your pH, obviously. But then I said to them, how much OH minus concentration is in there? And a lot of them said none. Because do you see any OH minus concentration in there? No. But you know, if you can calculate pH, you can calculate OH minus concentration, right? Where does the OH minus come from? Where does it come from? It's not here. Where does it come from? The water, the aqueous. And that is this KW thing. So KW exists in any aqueous solution. And we talk about it with acid, we talk about it with base, because you have an OH minus even though it's not obvious that you do. Where does OH minus come from? Water. 1 in a billion molecules dissociate. Okay? So that's, you know, in Chem 20 you just take it verbatim, but in Chem 30 you start to understand, oh, that's because of this KW thing. And you're supposed to tie them both together. Okay, so we've got that expression, we've got, by the way, maybe we should write all of our pH expressions here. pH equals negative log concentration of hydrogen. What other formula do you know? POH equals negative log of hydroxide concentration. What other formula do you know?
pH plus pOH equals 14.
Another formula?
10 to the power of negative pH equals.
Anything else? Same thing for POH. And concentration of OH minus times concentration of H plus equals 1 times 10 to the power negative 14, which actually is KW. So therefore, if we have it at a different temperature, the value is different. So it's actually KW that equals H plus times OH minus. And for Chem 20, KW is always this value, 1 times 10 to the power negative 14. But now we know that changing temperature can change our KW value, and therefore we could have a different number there if we needed to, or if they told us to.
Also, would you put in like the Ka equals concentration of
Yes, yes. Let's do K in a second. So these are easy money. If they give you a concentration of and they ask for the pH, that should be a very fast, easy mark for you. Okay, this is the I just want to pass. You better know these. Okay, boys at the back?
Yep.
Okay, so that's KW. Ka, what's the general expression for Ka?
H3O plus concentration times H.
Okay, note that these sides are equal in their charges. The top charge is balanced, the bottom charge is balanced. That's how you maybe can put them together. A positive and negative make neutral and the bottom's neutral. Okay? And what's the general formula that goes with Ka? As in what plus what yields what plus what? HA plus water goes to H3O plus and A minus. Does anybody out there not know that H3O plus is the same thing as H plus, and why? Everybody okay with that? You see them as the same thing now? They don't look foreign anymore to you? Okay, so that is Ka. You've got to know that like the back of your hand, because it makes these questions really fast. And that these two concentrations are equal. And so this is often x squared, and this is often a number, and this is often a number, and you solve for x, and you can find pH. You see how fast that was? Okay, so that is a golden easy answer, which is, I think, your last question on that unit exam, or maybe second last question or something. It's at the end of the unit exam, that's all I was asking for that benzoic acid. Okay, so Kb, what's Kb? Concentration of OH minus times concentration of HA all over the concentration of A minus. Note the top is a negative charge and the bottom is a negative charge. And the general formula for Kb is A minus plus H2O goes to HA and an OH minus. Okay? So you got to see them as separate. A lot of people, even though these are conjugate acid-base pairs here and here, and you look them up in the data booklet under conjugate acid-base pairs, it's not about, the Kb is not this reverse reaction. I'll say that again. The Kb is not these things going this way. The Kb is a completely different reaction. What is the reverse reaction? It's 1 over the forward reaction. This isn't 1 over, this is 1 times 10 to the power negative 14 over. Different. Different number, different value, different reaction. Okay?
Can you say the reverse reaction?
Yeah, so K for the reverse reaction equals 1 over K for the forward reaction. If you're going on the equilibrium arrows, where this is the K forward and that's the K reverse. All right? Which probably, I suppose, goes in our first sheet there.
So
really.
it's just that whole like HA plus H2O over 1?
Yeah.
Under 1?
Yeah. No, well, it'd be that value. So if I told you
Yeah,
that that
yeah,
was
that's
1
fine.
times, yeah. Okay? Any other questions? Craig, you paying attention?
So is Kb just, would it just be like your Ka, Kw divided by
KW divided by Ka, not 1 divided by.
Okay.
It's not the reverse of Ka. Although we tend to think of it that way, and I think that that misunderstanding comes from every other data booklet table that we have. When we look at the other side, it's the reverse of that data booklet table. So the strong oxidizing agent, strong reducing agent, they're always opposite of each other, and then the reverse reaction is the only one that, but that doesn't apply to our Ka-Kb table. So I think that that's where our misunderstanding comes from. We've recognized the pattern and then we just apply it there. No. Kb is a completely different situation. It's saying if I have that base all by itself in water, what's the equilibrium constant? The Ka value is if I have that acid in the equilibrium constant, what's that?
So these are all for the acids, right?
That's right.
So these is the Kw divided by this.
That's right. Yes.
And so just to clarify, to know, so the H3O plus concentration in the Ka equation
Yeah.
is the Ka value, or no?
No. The H3O plus concentration
Would be
is the Ka value times the initial concentration of the acid square rooted. Okay, KW, KA, KB, KC sorted. Good. So then acid-base equilibrium. This is kind kind of more just ice tables, although we did ice tables for the other ones as well, right? So acid-base equilibrium, there's only one proton transfer. Right, so sometimes you've got to figure out which is your acid, figure out which is your base, figure out what you're going to transfer the proton to what. Remembering water can do both. So sometimes water is involved. Okay, so they could throw you a very obvious question like, what's the reaction between ammonia and that in aqueous solution? And you could waste your time listing your species, looking them up on the table, where's your strong, but it should be obvious. You should know that these are both stronger than water, that this is going to be your strongest acid and this is going to be your strongest base. And therefore this is going to accept a proton and become NH4, pardon me, plus, and that's going to have lost the proton in HSO4 minus. Okay? So it could be that obvious and that easy. Or it could be not so obvious, and they could say, look, you've got HSO4 minus, you've got HCO3 minus, and in an aqueous solution, what's your reaction? Now for that, you're going to want to go to the data booklet. You're going to want to figure out which one of these three things is our strongest acid, which one of those three things is the strongest base, and then transfer your proton from your acid to your base. Okay? So if it's obvious, just do it, and if it's not obvious, look it up. Tallest on the left-hand side of the data booklet, strongest acid. Like you would. Everybody okay with that? What else do we know about strong acids and bases? I don't know, but it's not on there, is it? Ice tables. So actually, let's do a whole other sheet about ice tables. We've kind of seen very straightforward ice tables where you've got A plus B equilibrium, C plus D, initial change equilibrium. And they give you an initial, so they give you that this is 1.0 moles per liter, make sure it's in concentration, that this is a 0.5 moles per liter, make sure it's in concentration, right? So divided by 2 liters, if it says it's in a 2-liter flask, and they give you moles. Everybody okay with that? So sometimes that's one step you've got to make. And then often we start with 0 there, and the student allows it to reach equilibrium. They note that at equilibrium, C was, I don't know, 0.02 moles per liter. Right? Calculate the K value. Everybody okay with that? Everybody could do that?
Can you do it just?
Sure. So then you would need to say, well, the change of this was 0.02. The change of that is 0.02 if it's a 1-to-1 ratio. And these are also 1s, so this is, I must have reacted 0.02, reacted 0.02. So I take my 1 minus my 0.02, so I get 0.0, somebody help me. 0.98, thank you. And this would be 0.408. 48. And that's still that. And so my K value is going to be 0.02 squared over 0.98 times 0.48. Tappity tap answer. No units in this one because the units all cancel out. Okay? So that's one example of a nice table. If they could make it more difficult by having this be 2 there, and so therefore that is still true, but going this way it must have been that times 2. So 0.04 changed because of that 2 there. It's a 1-to-2 ratio, not a 1-to-1 ratio now, so 0.02 to 0.04, not 0.02 to 0.02.
Did they ever give you options for the answers, like some with units and some without?
I've never seen that before.
It's just more about the numbers.
It's more about the numbers. Okay? Could they? Sure. I just have never seen it.
Yeah.
And when you get to university, they'll expect it on the written response, but yeah, but I've never seen it tested. But we've all actually been very good with our units, so I'm not that worried. Yes?
So they do like the reverse and give you the initial concentrations of your products and the equilibrium. and
Absolutely.
everything.
Absolutely. Absolutely. So I could set up the exact same ice table, only this time they give me these, so 1.0 and 0.2, and they tell me at equilibrium I face this. 1.0 is formed there, and so I do all the things again, and it's still products over reactants. Tappity tap tap, done. Okay. Another ice table would be the X's, right? These X's. So ICE for A plus B yields 2 C's. So in this case, they've given you a K value, okay? And they've given you some information about the ice table. Normally, it's just the initials. So normally they've said that this is 0.2 moles per liter, this is 0.2 moles per liter, and this is 0. Okay, calculate the equilibrium constants is what they want. Okay, so you're starting to panic a little bit, you're freaking out because there's not much to put in the ice table. That's when you start to do your X's. So this will change by 2x for every x and x that changes by. Your change column is always about your ratio. The ratio bit, 1 to 2, 2 to 1, 1 to 1, always goes in this change column, never anywhere else. And so therefore this would be 2x, this is 0.2 minus x, this is 0.2 minus x, because I'm reacting about that and reacting about that. And so the K value which they've given to you, so it's just a number, equals 2x squared divided by x squared. I know, look, square to the top, square to the bottom. So actually, if I square root this whole thing, those x squares cancel and square root that thing. So I've got my square root of my K value will equal 2x over x.
Why is 2x on the bottom?
Yeah.
And then 0.2 minus x.
Oh, thank you, thank you, thank you. 0.2. 0.2 minus x. Thank you. And now I've just got some quite simple solving of x to do, as opposed to with that squared in there, it was complicated. Not impossible, just longer, takes longer. Okay, and if this is a numerical response, if this is not a numerical response, pardon me, if this is a multiple choice, if I wasn't able to easily cancel it out and I was going to my quadratic, I would take the multiple choice answer and I'd plug it in and I'd see if I get the K value, which is probably faster than doing the quadratic. Does that make sense? Okay, if it's numerical response, you're going to have to do the quadratic all the way. But if it's multiple choice, I'd probably, by this point, work my way backwards from the multiple choice answer, plug in the numbers, it'll just be faster. Saving yourself some time.
When you're doing the, when you multiply the 0.2 minus x up,
Yep.
when you're subtracting on the other side, once you're trying to isolate for x,
Yep.
there's like a certain, I don't know, there's something, one of the questions where you have to,
Okay. I'm just going to keep going because I've got 2 minutes left. So Bronsted liner acid base, that's about the proton transfer, proton acceptor. Titration curves, weak acid to strong acid, buffer zone only at the initial bit, equivalence point. We're okay with titration curves? Titration curves for diprotic. Yes? Yeah, 2 humps. Ride my train first, Emily. Amphiprotic, what's amphiprotic mean?
Pardon?
Yeah.
Give or receive. So an example of anti-product,
CH3CO.
CH3COO minus. That's a funny one. How about HCO? How about HOOCOO minus? That could give or accept, okay? A much faster one would just be your H2SO4, but lose an H and put a minus. Buffers. Buffers are hard because they're the last thing we do, not because they're hard. Okay, but it's because it's the last thing you do, and so you sort of just aren't paying attention. It's the combination of a weak acid and its conjugate base. How do you know what its conjugate base? Look at the data booklet. If you can't figure it out, lose one proton. That's it. And that has to be a salt. So chuck an Na plus or a K plus or a Ca2 plus on it. That's a buffer. An ice table for buffer is hard because you have an initial here and an initial here. But no initial on your H3O plus. And indicators are about those colors, picking an indicator range. I think we're pretty good with indicators. But I think you could probably do with some work on the buffers, just another look at it. Yes?
Just for the buffer one, that's when you kind of assume that the change is like measurable, right? Like
Right.
It's over the initial comment.
That's right, and they often use Le Chantier in their question. A little change because.
And do you assume the change is 0 for products only?
Pardon?
Do you assume the change is 0 for products only?
Yes. For a buffer, yes? Is that what you're talking about, Abby? Yes.